Okay, so I want to welcome you all to our November bios. We had two this month in the Biostatistics seminar series. We've got Wensong from FIU today, and I'll tell you a little bit about her. And then I just want to remind you that we have Edwin Iverson from Duke University later in the month, I think around the 29th or so of November. So Wensong is at our I guess our sister institution at FIU, in their Division of Statistics in the Department of Mathematics and Statistics. She's been there since 2011, and she's an assistant professor. Before that, she finished up her doctoral work at the University of South Carolina in the Department of Statistics, and she worked with our good friend Edsel Peña. So she got her master's degree there as well as her PhD degree. And prior to that, she got her degree in computational mathematics at Nanjing University in China. So she's kind of progressing in her career now and working on some really interesting problems. And what she lists as sort of her major methodologic areas of interest are sort of Bayesian methodologies in hypothesis testing, high-dimensional model selection, and statistical learning theory and application. So a lot of things that, again, are kind of common with a group of people in our department. So welcome, Wensong. So today she's going to speak about Bayes' multiple decision functions and classification problems.
Thank you very much, Dr. Rao, for the invitation and the nice introduction, and thanks everybody for coming. Today my talk is the Bayes multiple decision function in classification. So the title, I know the title is a little bit dry, not sexy enough, but I'm working on picking up a nice title. But this is a joint work with my former advisor, Dr. Edsel Peña at University of South Carolina. So let's look at the problem I'm dealing with. So this is a type of classification problem. Let's just put it into a case of diagnosis of a disease. So for a certain disease, suppose we have capital N subjects in the training set where we observe both the response, which is whether this subject has the disease or not, as well as a couple of traits of the subjects in the training set. So these traits could include their age, gender, or the presence or absence of some symptoms, or clinical tests, or even a genotype of activities. So we completely know who's sick, who's not in this training data set. Now let's say there are a couple of new subjects coming in, capital M of them. And for these people, we only know their traits. We can measure the traits, but we don't know their class membership or whether they have the disease or not. So that's our goal. We would like to predict who have the disease or not on predicting the variable of W. So the dimension of the W is capital N. That's our dimension of the problem. And we want to make the prediction simultaneously. So this problem is slightly different than the usual classification problem because usually you will see your data in the training data sets, but for the new subjects, you only look at one by one. So you look at a new coming in subject and to predict whether this person is diseased or not. But now we have a group of new subjects and we want to do the prediction simultaneously. So that's the main property of this problem. So this is what I call multiple binary classification problem. So generally, we'll start with a capital N, that's our dimension of the problem, could be large. The data include three parts, just as what we saw earlier. The X, Y are associated with the training sets. V are the traits or the predictors of the new coming subjects. So the goal is to make M classifications on the vector of W. So the coding for W and Y follow a conventional interpretation. If such subject is in a positive state or they belong to a positive class, then we say W is 1 or Y is 1. Otherwise, if this patient is in a negative state or subject belongs to a negative class, then we say it's 0. So we want to predict the 0, 1 value, or yes or no type of question. And we assume a parametric model. So this is the multiple binary classification problem. And this is a high-dimensional classification problem, and it can be used in many other areas, not just the diagnosis of disease. So it could be applied to, say, admission of the future students based on their records now up to the high school, as well as the records of previously admitted students. So maybe in a couple of years, you're going to measure are these students' success or not in the college life. So you can learn what are the good traits you can make your prediction. Or in the financial world, if there's a bunch of applicants who apply the credit cards, you need to decide who to issue these credit cards simultaneously. And say where to drill the oils among many potential sites. So these are just applications, and as you can see, I pick up the diagnosis of disease because you guys are from the biostat world. So depending on whose audience is, I'll put the problem into different contexts. So the framework I'm using is the decision theoretical framework, which is a little bit theoretical than the most people who are familiar. And then I'll use the Bayesian methodology. I guess is most people are familiar with. And the issues I would like to solve include these three. First of all, since I have a group of new subjects coming in, how can I measure the accuracy of the classification? And under that specific measurements of the classification, what are the optimal procedures? What are the best classifiers? And how to implement those classifiers efficiently. So let's start looking at some elements in the decision theoretical framework. This is just a very straightforward framework to look at. So we want to make our predictions. So if we want to make the prediction of Wn to be 1, which means the M subject to be diseased, then our action is 1 also. So we have a vector of zeros and ones. So that's our decisions, our predictions. So this is our goal. We want to cast an action vector of length m of zeros and ones based on the data. So if you just blindly guess who's sick, who's not, then there's actually totally 2 to the m different action vectors. Because if you look at the action vector, each position, say A1 has 2 choices, 0 and 1. Then A2 has 2 choices, 0 and 1. So totally there are 2 raised to the power capital M different action vectors. And our classifier can be described through the multiple decision function, delta, which is just a mapping from a piece of data into a specific action vector. So we need to pick up the goods, the best vector of the action in the action space. So that's our goal. Well, we need a way to evaluate the goodness of the action. So we have the truth of W, 0 and 1. We have a vector of actions A, 0 and 1. So how can we measure the differences between them and how bad is our action away from the truth of W? So I propose this general form of loss functions, which is a linear combination of 2 types of error loss. And they are weighted according to a predetermined cost ratio. So these 2 losses, L0 and L1, are associated with the false positive and false negatives in the classification. So it's just like a type 1 error, type 2 error in a hypothesis testing type of problem. So our goal is to come up with a procedure that can minimize such loss on average when you specify what type of error rates you are interested in and what's a good predetermined cost ratio. So the choice of lambda determines on your evaluation of the type 1 and type 2 loss. So if you consider the type 1 error loss, which associated with the false positives are more severe, then you can choose lambda to be large. If you think type 2 error of loss, the false negatives are more severe to you, then you can choose lambda to be small. So it's a very flexible type of loss function. Well, the L0 and L1 are not just any loss function you can think of. They must satisfy some conditions. So these are the technical conditions of the L0 and L1, but I'll just show you a couple of concrete examples. So for the false positives ones, you can consider the proportion of false positives among the capital N. How many are false positives, the wrong ones? Or you can look at the ratio of the false positives among all the positives in your prediction. That's what we call the false discovery proportion, So that's popular in the world of hypothesis testing. Or you can look at the false positives among all the non-true zeros, the non-true ones. So that's the false positive rates. Or a more familiar connection is actually 1 minus specificity. That's 1 minus the probability you're going to pick up the true positives given this person is truly positive. And there are just corresponding false negatives type of losses. One is the false negative, or false non-discovery proportion, or 1 minus sensitivity. So you can actually choose any pair from these two classes and form the loss function accordingly, weighted with constant lambda. So that's the loss function I'm considering. Now let's specify the model. So let's assume the marginal distribution of the x and v, which are the predictors or the traits, follows distribution g with unknown parameter eta. So it's a parametric model with unknown parameter. And the conditional probability of y being 1 given the traits is described through a function phi. So you can think of this function phi as a link function in a generalized linear model. So say in a logistic regression, you can think of this phi as the inverse of the logit transform with the linear, the inner product between the x and beta. So here the beta in the logistic regression are just coefficients, logistic coefficients. They are unknown to us. So this is our model. But you can use other link function. You can even do not consider the linear combinations. You can consider a higher order. But this is the general model we specified. Same thing happened to the W and V, the new coming subjects. And so our unknown parameter has two pieces. One part is the eta, which is associated with the marginal distribution of the traits, the predictors. The other is the beta, which specify the conditional probabilities. So this describes as a joint distribution of the data. So as I mentioned earlier, our classifier, our procedure, is described through the multiple decision function delta, which is mapping from the data into the action space. So now we can look at the risk function of all possible multiple decision functions by just looking at the average loss. So a loss just specifies how wrong is a certain action vector A from the truth of W, but we don't know the W. So we take an average with respect to the data distribution. Now go to the Bayesian route, putting a prior on the parameter theta. Then we can look at the base risk. It's just one more layer of expectation with respect to the prior. So now we have this base risk. It just described what's the average loss for a given function delta. So the best function, best classifier, is this base multiple binary classifier, or I'll call it BAM-BIC later on. So this BAM-BIC is naturally to be defined as the minimum of the base risk. So it's just saying I'll look at all possible functions, all possible procedures. Whatever can minimize the risk, whatever can minimize the average, the loss, is the best procedure. So that's just a natural definition. But this definition is not calculatable right now because it's a minimization over a function space, but we can do a little bit simplification of the base risk. So first of all, you can interchange the order of the integration. You notice to minimize the base risk, it's just equivalent to minimize the inner piece of the expectation, which is the posterior expectation. So let's just look at this posterior average loss for any action A. So this L tilde is the key. So for any data I see, this S is our data, I can calculate the average loss of any action A. So this describes the average of the loss for any action A, because we actually don't know the value of the W. So this describes how bad is A if I see the data S. So naturally, the best action would be the minimizer of this posterior average loss. So we try to minimize this overall action spaces. So the naive way is we can calculate this function for all possible actions and find the one that minimizes the average loss. But it's still not very clear from this the formula here is not very clear how to calculate this posterior expectation. So we actually simplify a little bit. If we can actually show if the prior specify the independence between the marginal distribution of the X and V and the the prior distribution of the beta, which is the coefficients, then we can simplify a lot this base posterior average loss. It can be simplified into this form. It has two layers of expectation. So the inner expectation is taking the expectation of the loss with respect to the posterior when we know the beta. So when we know a beta, then we can take the average with respect to the W given the traits for the new coming subjects and the coefficients. Then the outer layer is with respect to the posterior distribution of beta when we see the training data sets. So this is a very neat way to calculate the posterior average loss. So if you have a model, you specify your prior, then there's always the computational way to calculate this posterior expectation. So overall, our base optimal action, the best action, is the minimizer over all the posterior average loss. So now our bandBIC has this form. So when we see such data S, I calculate all possible loss functions with respect to all this action vector. Then I'll look at all of them, pick up the smallest one among them, and the A that gives me the minimized value would be the best action. So it's just a natural way. However, here's the technical difficulty. As we just mentioned earlier, there's actually 2 to the n different action vectors in this space. So there are many different action vectors you can choose. Is it necessary for us to calculate all the L tilde, all the posterior average loss for all possible actions? That's a lot of calculation. And just to emphasize how trouble it is, how much calculation difficulty it is, so let's look at how big is 2 to the n. So if you have 4 new coming subjects and you want to predict are they sick or not, there are actually 2 to the 4th, which is 16 different action vectors, 0s and 1s of length 4. If you have 10 new subjects coming in, you can actually have different, more than 1,000 different action vectors to predict. You want to find one of them. If you have 20 subjects coming in simultaneously, then you have over 1 million different possible action vectors. But there's always one that's the best among all that gives us the base optimal action. And we are going to find that one. So this is actually a needle in a haystack problem. We're going to find that needle among all the posterior average loss. So that's the difficulty. However, we propose an efficient search for this base optimal action. And by doing this procedure, we can save the computational cost. So we can use search the best one with a fairly low computational cost. So I'll just illustrate this algorithm in a concrete example. Suppose we have capital M equals 7 new coming subjects, and we want to make the prediction on those 7 subjects. So totally there are 128 different action vectors. So for each action vector, we can calculate the posterior average loss. And let's slice the entire action space according to the number of ones in our actions. So this is the class, this is a subspace when the number of ones in the action is 0. So this corresponding to the action vector of all zeros. So it predicts all 7 patients are no disease or healthy. Then this is the average loss by doing this. So you can calculate this. And for the number of ones in A equals 1, this means we're going to predict only 1 subject to be the diseased patient, other 6 are healthy. Then we can calculate the posterior average loss for these. So this is the calculated posterior average loss for all actions and sliced according to the number of ones in action. So this first step of the search comes just naturally within each sub-action space. Let's find out the best action that can minimize the loss within the sub-action space. So we can find out the bottom dots within each slice of the action space. So this will give me the best action if I'm gonna predict only 1 patient to be diseased and all 6 others are healthy. And this is the best action because among all the actions here, this gives me the lowest posterior average loss. So this is the first step. Then the second step is just to find the best among the bests. So that's by looking at across all the sub-action space, I can find the lowest among all the lowest. So the beauty about this search is that the first step can be done with nearly no cost. So with the loss function of the choice of yours, then this first step can be done very easily. And the search for the best among the best is very easy to do because now we only have actually 8 candidates, and we're going to find 1 out of the 8 instead of 1 out of the 128. So generally, the searching order of this algorithm is reduced from 2 to the m down to up to m squared log of m. And in many cases, this search order can be even reduced. So this is an efficient way of searching for the base optimal action. Okay, so let's look at some examples with the explicit form of the Band-Vic. So let's start with considering the pair of the loss function of the false positive and false negative and weighted according to constant lambda. So if we consider our best procedure, the Band-Vic under this loss function, then all we need to do is to calculate this posterior expectation. So this is expectation of that link function. So this is actually the posterior probability that W being 1. So this is the posterior probability the new coming subject is sick. So this, based on this posterior expectation, we just compare each of them with a certain cutoff value. And this cutoff value just depending on the cost ratio lambda. So this is actually a naive Bayes classifier. It's a simple decision rule because the decision of the nth patient only depends on the traits of this patient. this subject. It's not depending on all other subjects in your new group. Well, if you start with the loss function of the 1 minus specificity and 1 minus sensitivity, if you consider the bandwidth under this loss function, then the calculation is different. You need to calculate the posterior expectation of that big chunk. And if this posterior expectation is negative, you're going to predict this subject to be 1, to be sick. So if you look at the cutoff is 0, so it's still not depending on all other patients. However, the calculation of the DM, the nth subject, depending on everybody. Because if you look at the inner function, the integrant, it's actually depending on all the Wm from 1 to capital N. So it depends on all the subjects in your new group. So the prediction of the first subjects in your new group, depending on all other subjects, their traits. So this is what we call the compound decision rule. Look at the linear combination of the false discovery proportion and false negative. So this is a more used type of loss function in a hypothesis testing problem, the multiple hypothesis testing problem. Then we can calculate the same posterior expectation of W being 1. So those are the fees. And our decision rule looks like this. So we calculate the fees, which is the posterior probability of W being 1. And we're going to predict the nth subject to be 1 if it's bigger than some cutoff. Otherwise, if this posterior probability of 1 is small, then we're going to predict it to be 0. But this cutoff is actually depending on how many ones you're going to make in your action vector. And it determines by this formula of a k-star. And the determination depends on everybody. So it's saying the calculation of the phi m depends on only that subject's trait. However, the cutoff value depends on everybody's traits. So it's again another compound decision rule. So you may be curious, what's the good or what's the bad? What's the advantage of doing a compound decision rule compared to the naive Bayes classifier? Well, this is just showing the different aspects of the problem. If your model or your prior specifies some association between the marginal distribution of the traits and the conditional distribution of the response given the traits, then by looking at more subjects in your new group of the data, then you learn more about the marginal distribution of the X or V, so that it can transform into the prediction of the response. On the other hand, even if the distributions are totally independent, the priors are independent, we still have different decisions based on different subjects. That's the compound decision rule. But how good, why this is better than the simple rule? It's just saying if I have a group of new subjects, even if I do not learn any information from the marginal distribution, I can still try to make the best decision that can control or minimize the average loss with these capital M of the subjects. So the distributions of these subjects matters. If two subjects in your new group are having similar traits, then you're better to predict them to be the 1 or to be the 0 at the same time. So when you do the simultaneous decisions, you should have a more tendency to put them into the same class. Instead of looking at the simple decision rule, you shouldn't just look at them one by one. Because if they are close, they should be classified into the same class. So that's the good thing about the compound decision rule. Okay, just a few words about the posterior computation. That's not exactly what my specialty, but I'm sure here there's many aspects of the posterior computation. So generally, we need the posterior expectations of the form like this. So specific forms of the function of h looks like either it's w or the vector of w divided by the sum of w, or a vector of 1 minus w divided by sum of 1 minus w. So we need posterior expectation of this form. Even with the independent priors, the posterior calculation is still not analytically feasible, unless it's a very simple model. So if you specify a difficult model, or your dimension of the trace is high, then there's no way you can calculate this posterior expectation just analytically. So you need some approximation techniques to do the sampling or the Monte Carlo approximation. So there are many different types of technique we can use. But in my framework, in my decision function, I emphasize on how to make the decision once you calculate those posterior expectations. So this framework can be adapted into different calculations of the posterior expectations. As long as you have a good way of calculating those, then this is the scheme on how to make the decisions. Okay, so let's look at some illustration by the synthetic and real data. So this is the example when I simulate the data. So the model is very simple. We only have one dimension of the traits. So you only have one x or one v. And the model is just a logistic with no intercept. So the link function is this inverse of the logic transform. And I generate the data when beta is 1. So the true beta is 1 for us. And in the procedure, I specify a flat prior of beta. So try to mimic a situation of a non-informative prior. So in this case, the posterior calculation is fairly easy because we only have one predictor, one dimension of the beta. And we apply our bandwidth associated with 3 types of the loss pairs as earlier. And first of all, let's look at the case when lambda equals 0 for all loss functions. So this is the default situation. You consider the type 1 error loss, type 2 error loss are equivalently severe. So under that situation, okay, this is a box plot of the simulated data, the training and testing. I can calculate the posterior probability W being 1. So the first box plot is that posterior probability according to the true value of W. So they are pretty well separated in this case. And then the other 3 panels of the plots are plotting the true probability of W being 1 versus the posterior probabilities. So the decisions are color-coded with the red and black. So you can see when we have the naive base prior, that's associated with false positive and false negative. That's this corner. So we predict all the subjects with the posterior probability of W being 1 bigger than 0.5 to be true 1. Otherwise, if the posterior probability is smaller than 0.5, we predict them to be 0. So that's just a very simple decision rule, and this cutoff 0.5 is calculated from the lambda. When lambda is equals 1, you consider they are equally significant, then the cutoff is just half. But when you look at the decision for under the loss function of FDP and Fn, then the decision is still monotone with the posterior probability of W being 1. We still predict the ones with a high posterior probability to be 1, the low posterior probability was 0. However, the cutoff is no longer 0.5. This cutoff is actually determined by everybody's posterior probabilities. So it could be different if everybody else has the different posterior probabilities. And interestingly, if you look at the pair of 1 minus specificity and 1 minus sensitivity, the decision is no longer monotone with the posterior probabilities. So look at this guy here. it actually has a little bit higher posterior probabilities compared to those guys. However, we predict this guy to be 0 and these red dots to be 1. The reason is under this pair of laws, we want to achieve the minimized loss function of the linear combination of specificity and sensitivity. So the final decision is not simply look at the posterior probabilities. So it's a little bit complicated compared to the earlier two. Okay, so this is, again, another way to see the difference across different loss functions. So I'm plotting the plot of the true W versus the V. V is the only trait in this simulated data. So again, generally we predict the subjects with a high V to be 1, the low V to be 0. However, there's a little bit different. If you look at this, here's these 2 dots, and that 2 dots, here's a difference. Well, what does it mean? This plot is created when the M equals 50, when I only have 50 subjects. And this plot is plotting the same 50 subjects, but actually we consider a group of 100 subjects simultaneously. So the decisions on the same subjects differ when we consider a different number of subjects in my new group of data sets. So that's the effects of the simultaneous classification. So they may change. And the same thing happened to the specificity sensitivity pair, but for the naive base, it's always the same. Okay, so let's look at the simulated data, but when lambda changes. Earlier we used the lambda equals 1, but to compare different classifiers unbiasedly, we'd better just look at the ROC when the cutoff value changes, the tuning parameter changes. So for this simulated data sets, these 4 procedures, 3-bandit and largest regression, do not differ very much. You cannot tell who is the best. And if I do the simulations many times and take the average of the ROC for 500 simulated data sets, the 3 of them, the FNFP one, the sensitivity specificity one, and largest regression coincide with each other. There's some equivalency within these 3 procedures. And the one minimize the loss with the false discovery proportion and false negative is different. And it's not very fair for this blue curve because this ROC is plotted with a scale of sensitivity versus specificity. So maybe if you look at the false discovery proportion, it's actually better than other 3. And by theory, it should be better than the other 3. But the implication is that there might be some equivalence under certain model, but so far I cannot prove it, but it's worth studying. Let's look at real data. This is a diagnosis of lupus disease. The data is, I get the data from Dr. Renee Herrera at FIU. But I think part of the subjects are collected here in this hospital. So in this data set, there are 152 subjects totally, with 122 case and 31 healthy. And they measured the activities of 30 different biomarkers. To my understanding, these are the activity of some RNA protein complex. And the goal is to tell apart the healthy and disease, as well as different types of the lupus disease by looking at the biomarkers, based on the biomarkers. So I just use this data set for testing how good my procedure is. So I randomly divide them into 2 pieces. 69 subjects belongs to the training, and the other 84 belongs to the new group of subjects. We want to predict the membership, the disease or not, for these 84 subjects. So this is a heat map of the data with 8 selected biomarkers. The reason why I chose 8 biomarkers is that the logistic regression actually fails on model fitting with all 30 predictors. So if you look at the data set, we have 69 in training, the sample size is 69, the dimension of the predictor is 30, and the data is highly correlated. So logistic regression cannot fit that model. So to start comparing the logistic regression with our BAMBIC, I just choose 8 biomarkers for now. So this is the heat map, and I don't see it. I don't think this plot is informative, but it's actually showing a little bit contrast of the color for the true disease patients and the true healthy subjects. So the upper portion are true healthy, these are true disease patients. You can see a little bit contrast, and especially for this predictor, this biomarker, the contrast is the most. Unfortunately, on this screen it's not very clear. Okay, so I apply regularized Bayes logistic regression. There are different types of Bayesian logistic regression available. But this is a newly published one, and the good thing is they published the R package. So I just use their code and trust this procedure is correctly implemented. So these are the posterior probabilities, or posterior samples of the coefficients betas. So you can see for number 3 and 4, they're actually clearly different from 0. So those are the betas. So for the 4th one and 3rd one and 4th one, among those 8 biomarkers, they seem significant from 0. But we do not do model selection here or variable selection here. Our goal is to do the prediction. So we use these posterior probabilities or samples in order to calculate the posterior expectations of the h of w, the function we mentioned earlier. So I use these as our particles from the posterior probabilities distributions. So we can calculate the decisions. And this is the ROC when lambdas or the cutoff for logistic regression changes. So for this data, the logistic is slightly better, but not very clear. But compared to the other 3, logistic seems a little bit better because it's a little bit to the left, like here, or a little bit up there. But this is only for this data set. And it's just showing they perform all good. So all 4 procedures are pretty good. The curve looks like as perfect as we can imagine. So the perfect one would go the rectangle one, but this is closely to the perfect. But when we include all 30 biomarkers, now this dimension of the predictors becomes 30. In the training, the sample size is 69. So the logistic regression fails to fit the model. And we use the same Bayesian logistic regression technique, and we found out most biomarkers do not have the distinguished power. Actually, the coefficients are fairly 0. But again, these 2 are pretty significant, and this is also a little bit significant. And these 2 are the ones we saw earlier in the 8 biomarkers I chose. So when I have these posterior particles from the posterior distribution of the betas, I can calculate the quantities I want in order to make the predictions. So this is the ROC for the 30 biomarkers. So no logistic curve here. And the 3 performs fairly close to each other, and they are just good. So as good as the earlier ones. So here is a summary when I just choose a certain values of the lambdas for a pair of positive, false negative, I choose the lambda to be 2. So it's just indicating that I consider the consequence of false positive twice as much as the false negative. And the specificity sensitivity coefficient is 0.5. So I consider these, I want to achieve twice of the sensitivity compared to the specificity. And the cutoff value for FDP and FN is a little bit tricky to choose, but I just chose it to be 2.5. And logistic chose to be 0.18. And these are the classifications. So all perform pretty well, and for logistic, it cannot take too many predictors, but Bayesian methodology can correctly fit the model, and the performance is pretty well. So the most commonly questions after my talk is the choice of lambda. So I'll probably just mention a little bit. So if your data set is big enough, you can use some, say, cross-validation methods to choose lambda. It's just like any classifier, you have some tuning parameter. Even with logistic, you need to decide a cutoff value in order to make a prediction. But usually sample size is not enough, so I suggest is you do some double dipping with your current data, but still need to adjust a little bit for appropriate lambdas. So here, what I do is I just divide my own training data set into 2 pieces, and just use that, just look at the ROC curve and just select the one that seems can achieve a certain sensitivity for me. So, but generally, that's still unsolved issue, how to choose lambda when sample size is really small. But the point here is that I consider this general class of loss functions. Once you choose the loss pair, and once you choose that lambda, the cost ratio, there's always best procedure. The bandwidth is always there. And I achieve efficient search for that best option, action. So, and we saw that different loss functions lead to different types of decision rules, and they could act differently. But they all achieve the minimum average loss under the loss you consider. So if you want to achieve the sensitivity specificity one, you choose that pair, then you choose your lambda, then I guarantee this decision rule is the best under that loss function. Some future research, this is actually an ongoing project. I'm still writing out this. So there are many things I need to do right now. But some future research include, we actually saw some connections between all different loss functions and the performance of the bandwidth. It seems like there's analytically equivalence under certain conditions, but I cannot quantify that exactly for a moment. And when the dimension of the traits, the dimension of the predictors is high, we can adopt Bayesian variable selection methodology, and assuming specific priors, or do a more regularization type of problem. But this can be adopted into different variable selection procedures. Or when the link function phi is not known, so you may choose between the logistic regression and the logit type of link. Then you can actually do a model selection or model averaging in the Bayesian world, and by putting the prior on different families of functions. So these are the future research I'm considering. So that's all, and I again want to thank Dr. Rao for the invitation, and thank Dr. Herrera for providing this lupus data. And here's the paper, the new paper I referred and used their algorithm. So that's all. Thank you.